Hi, my name is Cam Thomas. This is my Physics 2 Lab 4 report on Faraday's law. This lab's purpose is to observe the interaction between a tube of aluminum and a bar magnet falling through the center of the tube. Using 5 trials, we will study how induced electric fields and drive currents from the fluctuating magnetic fields compare within both the computational data and the experimental data. Some assumptions we made is that there is a negligible amount of air resistance, only gravity and magnetic forces are present, and the bar magnet is treated like a dipole. The system is the bar magnet in the tube, while the surroundings is everything else. Some of the formulas and theories we are using in this lab are Biot-Savart law, Faraday's law and Lenz's law, and magnetic flux formula, with all the formulas to the right of them here. These are the results of the 5 trials in the experiment. We got an average of 0.324 seconds, and these are the some of the information we use for the computational model coming up next in the coding. This is the code itself. Mainly all this is just used so we can get our graph and visual model in the next slide. Here we can see the visual and the graph created by the computational model. Ideally, the graph would be completely flat going through the tube, as gravity and the magnetic force should equal out, making a constant velocity. But the computational model doesn't cover everything, so we weren't able to see that here, unfortunately. But we did get a time of 0.287 seconds. So for data, potential errors, and conclusions, we got a potential percent error of 12.89%. Some potential errors are not including air resistance in the computational model. The magnet could have touched the sides during the actual experiment itself when it was going through the tube. And it could have been some mismeasurements of time during the trials. Our conclusion is that there was a noticeable discrepancy found in the experimental application of the experiment compared to the idealized computational model. To start our discussion, we have red and blue indicate current flowing in opposite directions, which color corresponds to the clockwise current, and which is counterclockwise, and how can we know? So looking through the Lenz law model, we can find that red depicts going out of the page, which is counterclockwise, and blue depicts going into the page, which is clockwise for the respective currents. What would happen if the magnet poles were flipped going through the tube? The magnet would still fall in a very similar way, but the current induced will be the opposite of the original direction before it was flipped. For our next part of discussion, we have how does the computational model compare to the experimental data and total time for the magnet to fall? The computational model was noticeably quicker than the documented experimental model or data. If air resistance was included in the computational model as well as reduction of the possible errors mentioned previously, the model could have been much more accurate. What does the shape of the velocity versus time plot tell you about the forces acting on the bar magnet? Gravity is the primary force on the magnet while entering and exiting the tube, but whenever it's going through the tube, magnetic force works to balance out the force of gravity acting on the magnet. To start our what if, we have what if the resistivity of the conductor were reduced as close as possible to 0? How would the dynamics of the falling magnet change? With a very low resistivity, the induced current will have to increase to compensate. The magnetic field will strengthen and cause the descent to slow further. And we have this formula here to show it from the Ohm's law. For our next what if, we have what if the holes or slots were cut into the tube? How would this affect the ring currents in your model? The current will be separated into sections with holes or slots and create a weakened magnetic field. Gravity will be opposed less by Faraday's law, meaning that the magnet will fall through the tube at a faster rate than previously. Thank you for watching.